The exams are not graded yet. They just gave us the stands yesterday, so it'll be a couple more days. So I haven't even looked at them really, but we'll try to get those done hopefully by the end of the week is kind of my rough goal. Other logistics, the next homework is online. It's a big homework. I think I'm going to extend it a couple days to turn it in, probably till Tuesday or Wednesday, just because Monday's a holiday, and this lecture is going to cover the majority of what you need for the homework. So, and I don't know if I'll get through it completely today. So for that reason, we're going to extend it a couple days. What else? If you took an exam and you had a hard time, please come to office hours and get help. I had one student say I don't have office hours. I do have office hours. You just have to click the thing and make an appointment on when I'm available. Hotter is the same thing. It's a Google Calendar with when we're available. We're both available. I'm available for I think it's like 7 or 8 hours a week of office hours. So that's a lot of office hours. And but I do want to encourage you to go to Hotter first. He has a big class, and I'm teaching the 2 classes. I think he has a similar number of office hours, if not more, I think. But you have to schedule an appointment, and they're 10-minute slots. So, but obviously we can go a little long if you schedule it. It doesn't have to be restricted to that, but a lot of times it's simple questions that can be addressed quickly. I also have one time that pops up between meetings that is my only meeting Wednesday afternoon that I probably don't want people to do. So if you see you can see my busy time, or if there's one meeting like in the middle of nowhere, don't schedule that. I might have actually scheduled something to block it. So, okay. So last time we talked about buffers, and I know nobody paid attention to anything I said. I'm going to say that because you had your exam coming up, and everyone was worried about that, and I said it wasn't on the exam. I'm not going to cover the buffer stuff again, but what I will say is that it leads into this lecture very well. And you're going to understand the buffer lecture better after this lecture too. So it's actually almost worth revisiting that because buffering obviously deals with a single gate, either buffer, an inverter, and sizing, whereas logical effort is actually going to deal with arbitrary gates. So any logic function of gates and sizing of those gates, including inverters and buffers. So it's going to be a general model. And the reason that the last lecture I think had a couple rough spots is because I introduced a model, and we're going to talk about that model more today in the more general case, which will help a little bit. So revisit that that lecture after this if you don't remember that. I can guarantee you there will be homework. There are homework problems on it, so you will have to do them on that. And as you know, what did people take away from the exam? What do the exams look like? Almost every one of those problems was very similar to a homework problem. They're slightly different, but you know the type of material that's on it. I actually did not throw a problem out of the left field too much. I think the only one that was really a little different was the vertical thing. But if you know the layout material, that should make sense. So other than that, everything else was almost very similar to problems on homeworks. This homework we have, I think it's like 10 problems and 2 alternative problems. I say the last 2 are optional because they kind of repeat some of the other problems. But I put them there just because I had them, and I'm like, I'll give you more problems. But you don't have to do them for the deadline. So they're optional. Again, I've had complaints that there's not enough problems to do in the class, so I'm giving you more problems than you probably normally want. Yeah.
Can you do those last problems to supplement the problems you skipped earlier, or is it just...
No. Do the first ones, and just make an effort on those, and again, it's completion based, so, okay. And this lecture covers, you have to go through all the material here before you'll know how to do that homework. So, we previously talked about transistor sizing in gates. So, sizing a NAND gate where you size the PMOS, or the NMOS bigger to account for the series connections, and the NOR gate, you do the same thing with the pull-ups. So we've sized transistors in logic gates, and we were able to make any, it's actually the next slide, we're able to make any gate basically have with S equals to 1, it'll have the same drive strength as an inverter, right? We scale up to account for the series connections and either pull up or pull down. For the parallel connections, we assume that one of them is on, and so that's kind of the worst case. And so from then, if S equals 1, everything is the same as an inverter. Same as S equals 1 inverter. So that's the key takeaway from the transistor sizing stuff we did, right? Any logic gate, and you've had to do that on your last midterm. Now, we've also talked a little bit about CMOS gate layout. That's not going to pertain too much here, but we did talk about parasitics a little bit. So internal capacitances of gates and how they can affect the delay. And that'll change a little bit how we do sizing. We also talked about interconnecting wires, and that's when the buffering came into play, breaking up long wires into shorter wires. So what we're going to talk about now is this formula, which I did introduce last time with buffers, but we're going to really use this a lot more here. So this is probably the 3rd or 4th time you've seen this plot in this class. So that means it should be important, right? It's multiple lectures. And what we're seeing here is that if S equals 1, I said that everything's going to be the same drive strength as an inverter. And so from that, you can say this R is the R of a S equals 1 inverter. So it doesn't matter what the logic gate is. And then if you scale up S, we know that the sizes of all the transistors scale up proportionally, and it basically changes that output resistance by that factor. It decreases the resistance by a factor of S. But simultaneously, as we increase the size of those transistors, we're increasing the source and drain area. Remember, there's the area beneath the source and drain into the substrate, and there's the area around the source and the drain that adds a kind of a sidewall capacitance. So every time we increase the width of a transistor, we also increase some capacitance too. That's the first component here, this parasitic component of the capacitance, CP. And that scales up with the size of the transistor. So even though we increase the size of some of the transistors, we also increase capacitance, so it's not a complete gain on the performance or the delay of the gate. In fact, there's actually a component where they cancel out. This R times CP is the parasitic delay component of a gate. That's the delay of a gate just due to driving its own output. So even if it has no wire, no fan out, a gate will have a delay. And it's due to that amount. It's fixed for a given gate. And then there's another component of this. That cancels out. Then there's another component of this, which is R over S times C out. That is the variable part of the delay. So if you're driving a fan out, you're driving a wire, some capacitance. That resistance also drives that output capacitance, but that scales with the width of the gate. So if you size up the gate, it's going to decrease that resistance and decrease that component of that delay. So the left part is fixed. The right part is variable with the size. And so what that means is if we plot this, we end up seeing this asymptotic thing where if you size up, S gets really big. Basically, the second term, the right term, becomes 0. Right? The limit as S goes to infinity, that R times C out over S becomes 0. Infinitely fast. But you become dominated by that left part, which is the gate driving itself. And so that's why we cannot improve a gate beyond a certain amount. But the question then is, how big do you want to size it? The thing that this ignores is there's also the input capacitance of the gate. So whatever is driving this gate is going to have some resistance and have some input delay as well. So this is only considering this gate itself in isolation and not the chain of gates or the inputs driving it. And that becomes a problem. And that's what we're going to talk about with the sizing problem. So think about this further. We can do some kind of fast timing-aware techniques by things like this. If we have, say, a 4-input NAND gate, it's not always best to size that NAND gate. If we want to pick this S, that might be a big gate that you have to pick to drive that big load. Because And it's just inefficient because first of all, you have to size up all of those transistors because it's a 4 input NAND. And you know in the pull down stack, the series connections, each of those is 4 times bigger than they are in an inverter. So it's very inefficient to size that gate bigger because it increases our area, right? So increasing S, that means increased area. And we're saying area, it can be approximated by the total width of all the transistors. So if I is in each transistor, right? That's just a ballpark saying, oh, if I have bigger transistors, I have a bigger gate. Whereas some cases, you're better off saying, oh, I'm just going to fix this as a minimum size gate. Keep it S1, keep it small, keep it efficient. And then over here, I might increase the size of these gates. Because those are inverters and they're very efficient to size up. And we saw last time that if you want to drive a big capacitive load, what do? You have a number of stages to ramp up the size to drive that load. So the overall delay of the right side, depending on what C is, can be much faster than the thing on the left. Now the question is when? When is this true? What values of C does that make sense for? That's what we're going to be able to do with this methodological effort. And I talked about the kind of single example with an inverter where we just kind of brute forced it number of stages and showed that it's kind of the log base 3 of this value. But we're going to drive that and use that for sizing these circuits. So what I'm going to do is we're going to now talk about delay in basically a process independent or a normalized term. So we normally think of delay as like 20 picoseconds, 1 nanosecond. We're now going to formulate everything as a fan out of 1 inverter delay. Okay, an inverter, smallest inverter, driving itself, and actually it depends where you look. Sometimes it can be a fan out of nothing inverter delay. It depends which context. But we're going to assume that that smallest gate with the smallest load has a delay of 1. Everything else is relative to it. So just like we scale sizes, not in terms of nanometers anymore, we say size equals 2. We're going to say delay equals 2. That means it's twice the delay of an inverter. Okay, and what is that value? It doesn't really matter what it explicitly is, but we're going to call it tau. This is the normalization constant. It's about in our in 180 nanometers, it's about 12 picoseconds. 130 nanometers is going to probably be about like 10 picoseconds ish. One of the old homeworks I used to have people do for the SPICE simulation is actually figure out what this tau is. I didn't have you do that on this homework though, or the last homework actually. So if we do that, then if we have any sort of absolute delay measurement, so let's say 100 picoseconds, we then know in 40 nanometer, actually it's going to be 100 divided, or sorry, 0.6 micron. It's going to be 100 by 40, which is 2.5 inverter delays. Okay, they're just normalized by some constant tau, and this constant tau depends on the process. Now, if we then reformulate this, delay now has 2 components. It shouldn't be a surprise. I just showed you on this previous slide. Here's 2 components. Here is P, and here the other one was F. Right? P is the parasitic part of the delay due to the gate driving itself. F is this variable part of the delay. So we're going to reformulate gate delays as that, F plus P. P is a constant. F depends on the size. It also depends on the function of the gate. And we're going to talk about that. So now that parasitic part is fixed. F we're going to actually call, there's a bunch of definitions we're going to come up with, which are going to sound weird at first, but everything is linear equations essentially. And I'll give a table of all of the terms at the end, and so you can kind of review them and have them in one place. F is going to be called the effort delay. And that's going to be, it has 2 components to it. G, which is actually called the logical effort. And actually we'll talk about this on the next slide. And H, which is the electrical effort. And the total effort, or the effort, just the effort, is G times H. It's the product of those. Now, why is it the product? Everything is going to be kind of 1 as a smallest value. And we're going to express everything as how inferior it is to 1. So if it's twice as bad as 2, 3 times as bad as 3. So for that reason, you can understand why a lot of times we're going to use a product, right? If we haven't told you what these are yet, but if the logical effort is 2, you know it's twice as bad as an inverter. And that should make the delay, this variable part of the delay, this effort part, twice as bad. So that's why it's a factor of how much worse it is than an inverter for each of these things. Actually, effort. Now, what are each of those components? Well, so G is the logical effort. And what this is going to do is it's going to measure the ability of a gate to drive an output load compared to an inverter. So logically, how bad is a gate compared to an inverter? How much worse is it than an inverter? So if G equals 1 by definition of an inverter, because nothing can be more efficient than an inverter. If I have a gate that has a logical effort of 2, its logical effort is twice as bad as an inverter, which means it's twice as inefficient at driving loads than an inverter. Yes?
What would be an example of that?
I'll talk about this exactly. I'll go into how to compute this and explain how to come up with it. But just kind of high level right now, understand what it's meant to do. Yeah. So this is how it scales compared to any inverter. Because the other component of this is the electrical effort. The electrical effort says how well does this scale compared to an inverter for an output load. Or actually, it's how much electrical work is this going to do? Okay, let's not even get into the sizes quite yet. You'll see how it gets into sizes. How much electrical work is this going to do compared to how big I am? So if I'm a tiny gate, do I have to drive a big output capacitance? If I'm a big gate, do I drive a little output capacitance? Just how much work am I doing? How overworked am I? And then again, I talk about the parasitic delay. That's just the delay of a gate driving no load. So it's that fixed component for every gate. This can be different for every gate, by the way, but and we'll talk about what that is. But each gate has a fixed delay that can't get faster than. So sometimes the electrical effort is also called the fan out. So we did like the fan out of 4 delay of an inverter. It's driving 4 copies of itself. So that by definition is going to have an electrical effort of 4. Right? So C out is 4, C in is 1, let's say. So it's a ratio of 4. Yeah.
So that does say that fan out is always proportional both to the output and input.
Yeah, the fan out is relative to the, because you asked me a question. I was unclear on the homework what the fan out dates should be on the last homework you did, where I think my solution had them all as inverters instead of copies of the gate or something. And so you can just define it as the ratio of capacitances. So if I have a fan out of 4, let's say 4 size 1 inverters. So let's say these are all size 1, and then let's say we have a gate here which is a size 2, and it's driving all these. In that case, the electrical effort is going to be 4 divided by 2. Oops. Because I'm having a bigger gate drive smaller fan outs, and so it's the ratio of those.
So that would be considered a fan out of 2.
It'd be an electrical effort of 2, but it's a fan out of 4. It's a number of gates, it's a fan out of 4, but in terms of electrical effort, it is 2. Now, what does this mean then? So we have this equation, GH plus P. What does that look a lot like? It looks like MX plus B, lines, right? P is a fixed number, except what is my X? Well, X is going to end up being H, kind of. But with lines, we can plot. And each function of a gate will have a different line that represents its delay. The horizontal axis is the electrical effort, so this ratio of the output load to the input of my own gate. And then the y-axis is the delay, normalized. So again, this is divided by tau, so it's not in picoseconds, it's in inverter delays. Well, obviously, we can look at the inverter line, and what do we have? An inverter without any output load, so the electrical effort is 0. C out is 0, C in is something, is right here. So you have a delay of 1. That's how we defined all the delays in terms of an inverter. What does an inverter with a fan out of 4 have? What is the delay? Well, it's somewhere right here. And if we can actually plug in and to figure out what that is exactly, where we're actually going to define it as G of an inverter is going to be 1, the P is going to be 1, and H in this case is 4. So GH plus P is 1 times 4 plus 1 is actually 5. So it's like right, you can't see it well, but it lines up right here, 5. That's the delay of a fan out of 4 inverter in any technology, 5. Now, how does this, I just copied this example of this kind of compact model of an inverter, or this is any gate now. This can be an inverter here, or any gate. Because now every gate will have some R where we increase the size S, it changes the resistance, it has that parasitic delay component, and it also has this input component here, which I kind of skipped over previously. Because remember, electrical effort is relative to that input component of the capacitance. Here you can see C out over C in. And so from that, you can also find that H is proportional to C out over S times C, or sorry, C out over C in. So what happens when you scale S? You actually decrease the H value. That is our X in the linear equation. So if I write out this whole thing, I can say G times C out over S times C plus P. S is my unknown variable, and then this is the X, actually 1 over X, and then this is the Y. Yeah. If you scale an inverter, the parasitic delay increases, yes. But the resistance also decreases proportionally, and they cancel out, right? Because R is over S, and S is times CP. So they cancel, and so that's why you end up with that fixed term P, which is a constant. Yeah. That happens for every other gate, too. There's a different constant term there. CP is different for every gate. Like an AND gate's going to have CP a little bit different than a NOR gate, an inverter. So that fixed term is going to be different for every gate, though. And you can see that with the y-intercept. This y-intercept right here, let me draw it this way. The actual y-intercept is P, which equals R times CP for a gate, right? Because the C out is 0, so that second part of the term doesn't matter. And so we can see for a NAND gate, what is the parasitic delay? It's 2. It's actually twice as bad as an inverter. Now, the G term then, so this logical effort, so that's the parasitic part P. We know the H is the electrical effort, so how well it can drive compared to how big its input capacitance is, and that scales with the size. We then also have the slope of this, either one. So this is our MX plus B, right? We have our B, which is that parasitic part. We have our X, which is related to the S, except it's 1 over S. And now what is the slope? Well, that's how much it scales compared to an inverter when we increase the size. So what I mean, and how do I figure that out? Well, I'm just going to say right now an inverter is going to be 1, and every other gate is going to be worse than 1. The question is, how much worse do they scale in an inverter? A 2-input NAND is going to be 4/3. I'll talk about why in a second. Yeah. So when you increase the size, what do you mean by better than inverter? So when you increase the size, you change the delay. Nothing can be faster than an inverter with no load. That is 1. Nothing can be faster than it, right? Because if you have a NAND gate with no load, it's going to be slower. It has 2 transistors in series. If you have more internal capacitance, so nothing will be better than an inverter. So if we're talking about delay of an inverter, it's always going to be worse. What happens if you size something up? Well, when you size something up, you can change the component of the delay related to the output capacitance. Again, we can go back to this plot right here. For any gate, if you size it up, it's going to make it faster. It'll approach some limit, and that limit is determined by how much internal capacitance that gate has, which depends on the function of the gate. A NAND gate, a 2-input NAND gate is worse than an inverter. A 2-input NOR gate is worse than a NAND gate. An XOR gate is going to be much worse than either of those gates. We're going to find how to compute that, how much worse, coming up. But the point is they're all worse than an inverter, but by how much? So hopefully that makes sense. Again, this is a lot of definitions, and then we're going to come up with concrete examples that will help make things make more sense. Because I think that's the most useful thing. So how do we compute this G? How much worse is it than an inverter? Well, we're going to define it as the ratio of the input capacitance of a gate to the input capacitance of an inverter. So remember, what is the input capacitance? Right here, it's this component right here, S times some internal capacitance. It's related to the size, but it's Cn. Now, all of this assumes beta equals 2. Remember in sizing, what is beta? It's how worse are PMOS than NMOS. Much less mobility is there in a PMOS than an NMOS. So this assumes 2. If we size an inverter then so that the P pull-up is the same resistance as the NMOS pull-down, we size it twice as much, right? So we did this transistor sizing. What is the input capacitance of this gate? Well, it's going to be 3. We're just going to total up the sizes of the transistors. So a size 2 transistor is 2, a size 1 transistor is 1, the total is 3. Now, when we sized a NAND gate, what did we have to do? Remember, we had to double the pull-down transistors here so that they have half the resistance so that that pull-down is the same as 1 NMOS. So we doubled them. We didn't have to double the parallel pull-ups because worst case is 1s on at a time. What's the input capacitance of a NAND gate? Well, you look in one of these pins and you see both of these. It's 2 for the PMOS and 2 for the NMOS. It's 4. If you think about that, it's more than an inverter because we had to double the size of that gate in the pull-down stack, right? Now, the definition of how something, and then remember, when we wanted to size these with S, you just scale them proportionally, right? So I'm going to kind of ignore that for right now, but just remember that that's how they scale up. So this is for size 1. But the same would hold true for any size S, except it would just be 3S and 4S. Now, if we do C in of the NAND gate relative to the inverter, we get 4 divided by 3. That means the input capacitance of an inverter, or a NAND gate, was 4/3, 33% worse than the inverter. Because we had to scale up that 1 NMOS by 2x. Right? We didn't have to scale up the PMOS. That stayed fixed, but the NMOS went up. So the initial size was 3 for inverter, and then we went and doubled one of them and added 1 more unit capacitance to that NMOS, so we got 4. So it's less efficient. Now, what did we do for a NOR gate? For a NOR gate, we had the same type of thing. Oops. Except here we had to double it because it's in series, and then double it because it's PMOS. So that's why it's 4x for those pull-ups. And so what is the input capacitance of the NOR gate? Well, it's 4 for one of the PMOS and 1 for one of the NMOS, so it's 5. And so what this says is, if we just look for size 1 of all these gates, a NOR gate is 5 divided by, relative to an inverter is 3, it's 5/3 for the logical effort. So a NAND gate is less efficient, but a NOR gate is even less efficient, right? It's another third less efficient. I see a couple hands kind of maybe stretching. Now, we didn't talk about sizes here. What changes if we have sizes? Nothing really changes. Like here, we would have 3s over 3s. Here we have 4s over 3s. They cancel out. Here we have 5s over 3s. It cancels out. S's don't matter. This holds for any size gate. Yeah. The last one's doubled because one of the doublings is because they're in series. So we have to make them twice as big to account for the 2 transistors in series. The other doubling is because the beta is 2. The PMOS are twice as bad as the NMOS. So then you have a factor 4 for those. Yeah. And remember, I can change beta. Like I can tell you beta for this process is 3. If you did that, then instead of being 4, it would be 6. Because you'd have 2 for the series and then 3 for the beta. So it depends on what the assumptions are. Different technologies have different ratios of performance of NMOS and PMOS. For logical effort, we assume it's beta equals 2 for almost everything. I can switch it up in the exams. Mental note, right? Yes.
Why CN4 and CN5 for both of those? I thought we just added up the sizes of it.
Yes, we add up the sizes. What is let's look at input A here. This drives a size 4 here and a size 1 here. So it's not all of the sizes. That's a very good point. It's one of the inputs. Very good point. In this case, also, notice A and B are exactly the same for both the NAND gates and NOR gate. I'll make a point on that because not all gates are going to have the same input capacitances for all inputs. I'll show you later, but think about an AND or invert gate. They have different sizes for the different inputs. They're not symmetric. Yeah.
If we, for whatever reason, put the NAND gate felt like not doubling the NMOSes and just dealing with the additional delay, would the logical effort go down and then something would have to go up, right?
So I guess you're asking if we don't double the pull downs in NMOS, let's say, so it's size 1 and 1.
Yeah.
Well, then your resistance is twice as bad as an inverter. So I guess your H would be twice as bad. You'd have to have 2H, or roughly. Yeah.
So you're saying there's other examples of if, for example, A has 5 inputs and B has 3 inputs?
I can go through some other examples. We can insert another example here. I'm going to summarize a number of gates, and I'll go through another example. How about that? Inverter. Let me insert it right now. What is it for a? What about for a NAND 3? What is the input capacitance of a NAND 3? So just do this. What would the pull-ups be? They're all going to be 2, because they're worst case they're in parallel. What do you have to do for the pull-downs? You have to do a factor of 3 because there's 3 of them in series. So each of these is going to be 3. So what is the input capacitance of, say, one of these? 5. What is the electrical effort, or logical effort of that? 5 divided by 3. So a NAND 3 has a logical effort equivalent to a NOR 2, right? 5/3. If I had the previous one, 5/3. So you get one more input out of a NAND gate that have the same logical effort as a NOR gate. What does a NOR gate look like? So we're going to have 3 pull downs, 3 series pull ups. So here's our NOR gate. What are the pull downs in a NOR gate? They're all 1, because everything is in. Let me circle this just to be clear. Now, what is about the pull up? Yeah, we have 3 in series times beta, so it's 6. Here we have 6, here we have 6. So what does the input to this look like then? CN? 7. So the logical effort for this is 7/3. I saw a 6/7 there. No. Yeah, go ahead.
This might be a silly question, but could you have a situation where different inputs and different capacitances?
Let's do one more example. Let's do an AOI gate. I think this will answer that question. So, or actually, which one is this? Is this an OAI or an AOI? I forget. I'm making this gate, and then the opposite will be this. This is an OR and invert, maybe. This is an and or, I don't know, whichever one it is. Depends on your nomenclature. So if this is input A, this is input B, here's input C, this is A, and this is B. How do you size these transistors? Well, C here is going to be 1, because it's just worst case pull down. What about the A and B NMOS? They're 2. Now what about the pull up? So the A and B have to be 4, because they're in series with a C, but they're PMOS. And then what about the C? Yeah, that's 4. Right? Yes. So now what is the input? Now I'm going to say, what is the C in of input A? Well, that's 6. So that means the logical effort, G, of input A is 6/3. What is the C input of C? That's 5. So the logical effort of C is 5/3. So that means the different inputs have different logical efforts. Yeah, because they're asymmetric. Right, yeah. Which one do you choose? The answer depends on which path you're thinking about. So the answer is depends. Yeah. The denominator comes from the input capacitance of an inverter. Always compared to an inverter, because this is how bad it is at scaling compared to an inverter. Now, how do they scale? Well, you can see we did a few of these. We did up through here. We can actually scale for 4 input and more. So NAND's always going to be n plus 2 divided by 3, and NOR is going to be 2n plus 1 divided by 3. Again, you don't go much past here, right? You don't go past 4 really, because it becomes inefficient. But you can do something similar with some other gates. And I put a couple here. So what about asymmetric gates? Well, I just did this. Here's some other weird gates. These are actually very efficient gates. XOR, while being mathematically interesting, scales horribly. So it has for 2 input XOR, it's 4. It's 4 times worse than an inverter. And then tri-state or muxes, those are constant. Now, why is this? Well, for a tri-state or a mux, the internal part of the capacitance, that CP, actually gets really big, we'll find out. But this part of it is actually pretty small. Now, how do we compute the parasitic part of the delay? So that CP part. Well, again, it's going to be related to the unloaded gate. You can either figure it out with basically you can figure out mathematically with the delay, which is kind of one preferable way to do it. If you look in the literature, there's numerous ways to define it, but they're all about the same. And in the end of the day, we're going to assume that there's simple constants for each gate type. An inverter is going to be 1. And so here, one way of defining it is you can say, okay, what is my unloaded gate delay compared to an inverter, right? Because what is my unloaded gate delay? Well, it's S equals 1. It's R times CP. So it's the resistance of the gate times the internal capacitances only. And so if we do that for an inverter, and we figure out that delay, and we do that for another gate, we just take a ratio of those. Because we sized the other gate to basically have the same drive as an inverter by scaling everything proportionally, the output resistance should be equal. And so we're just comparing that CP part, essentially. So this is an easy way to basically compute it just by doing a simulation and taking the ratio of the delays. I spelled this out last time, too, because I had homework where I made people do this in Spice, as I mentioned. And I want to make sure everyone uses the same definition. So this is all through self-loading. Now, how does this look for different gates, then? Well, when we look at the number of inputs in inverters, 1 by definition, both NAND and NOR are actually going to increase proportionally to the number of inputs. Now, why do you think that might be? Well, in both cases, we keep adding another series connection, either in the pull down or the pull up. Every time we add another series connection, that adds some more internal capacitance. Right? There's only one series connection, either pull up or pull down. So they both go up related to the number of inputs. And then here we see, XOR, XNOR had a really bad logical effort. It also has a bad parasitic delay. And a tri-state had a constant logical effort, but it has a really bad parasitic delay. So these are just other extreme cases. How would I do the parasitic delay of an AOI gate? Well, I do this formula. I measure an inverter. I have some delay. I measure the delay of the AOI gate, and I have another delay with no load. I take a ratio. What about the different inputs? Well, technically, the different inputs could have slightly different delays. So you could have a different CP for each input, technically. But we're going to assume kind of these constant values. These are also in the papers, the paper I signed for reading in this class. You should memorize this stuff. You should put this on your note card. I will not provide this on exams. You can put this on your table. The reason I don't put it is you should be able to derive it for most cases now, right? Based on the definitions I gave, P inverter is a little harder because you have to do simulation by my definition. But logical effort, you should be able to compute logical effort for any gate. All you have to do is size them so that they're the same as an inverter, and then do the ratio of the input capacitance. So you shouldn't need the table for the logical effort. All right. We got this fancy stuff, lots of definitions. Why does it matter? Well, let's do an example case. Let's say we want to make a ring oscillator. Someone was asking me the other day, how do we make an on-chip clock? Ben, you're asking how to make an on-chip clock? One of the ways is in a ring oscillator. You basically have a number of inverters. With feedback, you have to have an odd number of inverters, so it's a bistable circuit. If it initializes, first of all, it has to initialize some value somewhere. But once it does, a 0 will propagate through the whole thing, then it will invert, and then a 1 will propagate through the whole thing. And it will keep cycling through. It never reaches a stable state. It goes forever. That's why it's a ring oscillator. Startup has to have some conditions where it has to have the odd number of stages to have that. And technically, it could be that every stage is balanced at exactly the same point and never starts up, but that's extremely unlikely. Now, what is the delay of this? Well, this is the perfect case of using logical effort to figure out the delay. Because let's look at this. So we know that the delay of, or logical effort of an inverter is 1, right? The input capacitance is Cn. The input capacitance of an inverter is Cn. Cn over Cn is 1. We know the electrical effort is 1. Why is the electrical effort 1? Well, every inverter is fanning out to a copy of itself. So C out is the same as Cn. Right? We're assuming no wires here. They're all the same. So H is 1. We know the parasitic delay of an inverter is 1. We just defined that, right? It's how worse the internal loading delay is compared to an inverter. So what is the delay of one gate? Like, let's just take this gate. That's the stage delay down here. Well, that's going to be G times H plus P. 1 times 1 plus 1, 2. What is the delay through this whole thing? Let's say it's n stages, right? N stages. Well, it's going to be 2 times n for a 0 to go through. And then if we want to do a cycle, it actually has to have the 1 go through also. So actually 4 times n to have 2 loops through this oscillator, to have a full oscillation. Right? So the frequency is then 1 over 4n. So in this case, this is the number of stages, and this 2 is to make 2 cycles for the 0 and the 1, because it's an oscillator. And then d is the delay of the single stage, which is also 2. So it ends up being 1 over 4n. What this means is the frequency of this is directly proportional to the number of stages in my oscillator. Yeah.
Is that frequency in hertz? That seems very slow.
So what is the frequency? So remember, what are our delays? Our delay is defined as inverter delays. So it's in, not hertz, but inverter delays. What if we want to go to hertz? Well, we multiply it by tau. Actually, we divide by tau, sorry. If we want to know it in an actual frequency, yeah, tau is here, so it'd actually be in hertz, it'd be 1 over 4n tau. That's in hertz. And again, that tau is going to be pretty small, like 40 picoseconds, so that's going to put us up into the 200 megahertz for 0.6 micron. One of the old homeworks I used to give, I didn't give it to you, is I gave you a sizing problem, right? Balance the rise and fall. Another one I frequently do is make a ring oscillator of X frequency. You can either randomly try stages until you get to it, or you can do this and be like, oh, it's about here. Try one bigger and one smaller. Actually, 2 bigger and 2 smaller, you get an odd number. Just get as close as possible. Yeah, question?
Is it possible to do like the frequency changing after it's been fabricated?
That's a good question. So after you fabricate this, it's fixed. What can you do to, he's asking about basically how you change the frequency of an oscillator. Well, how do you think about it? Like, think about this in terms of what causes the delay. Think of Elmore delay. This is a good example of like using what you've learned to apply to things. How would you change the delay of, say, one of these stages?
Could you change the line voltage in the voltage response?
That's another way. You can change the voltage. What does changing the voltage for these do? That effectively changes the resistance, right? So we gave you that way of computing the R on value of your transistors. That depended on VDD. So if you change the voltage, that'll change R. What's another way? Elmore delay, RC. There's only two things. But one, you can change R. Capacitance. How can you change capacitance? What if I add a bunch of capacitors here that are, let me do it this way, that have a switch. So here, if I enable this, it's going to connect the capacitor. If I disable that, it's going to disconnect the capacitor. So you can add and remove capacitance electrically. So change the voltage, change the capacitance, even more than change the voltage. Actually, there's one third thing you can do. Yeah. Very similar. The crystal, a crystal oscillator will do that's used something like either a Colpitts oscillator or these different oscillator circuits. It still does the oscillation, but it is used to make an unstable feedback amplifier, essentially. This is kind of an amplifier, and it's unstable because of the odd number of stages. It's just that the gain of this is essentially 1, because it's an inverter. In that case, you'll make a gain of some value that's not 1. But it's an analog oscillator. That's what they typically do for most off-chip oscillators, because you have a crystal off-chip that you want to use. That can be better for higher frequency and more accurate clocks. This one is actually bad because of if your VDD varies, it changes your frequency. That's bad. So we changed R, we changed C. There's actually one other thing you can do to get a different frequency. What was the other thing down here in the frequency that I can change? So those both change D, the stage delay. N. What can I do with N? Yeah, what if I just, in here I took a mux, let's say, or let me just add a mux here and say, rather than taking it here, have a mux. A mux. It can either come from there, or maybe it comes from here. So if I can either cut it in half or keep the whole thing, right? That'd be divide by 2. Yeah. Not quite. PLLs will use these delays in them. I'm not going to get into a PLL for this, but you can use it. You can use these delay control mechanisms in a PLL to match the delay of another signal. So I'll say it that way. Yeah.
And this, if you have like hundreds of these, they sell like multiple like waves.
Yeah, if you have 2 of these on the same chip, they're not going to be in sync with each other at all, is one thing.
If you have like a ton of these inverters, you have like multiple waves within a single loop.
Oh, you're saying if I have these, I can basically tap off the clocks at different points? Is that what you're saying?
It's always settle into a nice like square wave.
It'll be,
2 times per second.
yeah, it'll be a nice, not perfectly square. It'll look kind of like your simulations, more kind of the exponential rise that fall because of the capacitors charging, discharging. So it won't be perfectly square, but it'll be,
It'll be like 2 switches per revolution.
yeah, higher than a low.
Weird intermediate ones.
No, because it'll be consistent. You have the same delay through these every time. So there's very little, very little variance in it. Yeah, unless something in the environment affects it. If I get what you're asking.
I'm wondering if it can like it toggle multiple times per going on.
Oh, if you could,
In a weird state.
no, it'll always settle into a state. I guess if you have one that's long enough, you could have multiple switchings at the same time, maybe. Yeah, like half of it going high while the other half is going high at the same time. Like 2, I get what you're asking. Maybe. There's a form of clocking that tries to do something with that. There's a whole field of clocking called resonant clocking. Actually, I did some research on it, and there's something what you're asking related to that, which is called a traveling wave oscillator, is I think what you're getting at. So you can have multiple of these waves at the same time, but that's another topic. Okay, so ring oscillator. We've now been able to design one to have a given frequency by a number of stages. One other question. What if I change the size of these? What happens to the delay? Or what happens to the frequency?
Should it remain roughly the same because the fan out and fan in are scaled together?
Yeah, it should remain roughly the same because the fan in and the fan out are roughly the same. Explicitly, we can go in here and say, where does that happen? Well, right in this term. This is the output to the input of a given stage, right? Well, if I double the size, the output capacitance doubles, but so does the input capacitance. So that H stays 1. What part am I ignoring, though?
The parasitic one?
The parasitic part. If I size this up, the parasitic delay may go up because that's proportional to the size. So, but that's a small part, but it may go up. Yeah. Okay, another example. Let's look at fan out of 4 delays. I mentioned one of the things I like to do when I get a new technology is I go to the lib file and I look up what the fan out of 4 delay. I find the capacitance of an inverter, then I look up in the inverter table and I say what's the capacitance for that fan out with some slew. That gives me an idea of that process technology. You can actually ballpark it with logical effort. If we look at a single inverter with a fan out of 4, we know that logical effort of an inverter is 1. The electrical effort is going to be 4 because it's going to be it's copies of itself, so it's 4 divided by 1. This is 1 here, and I have 4 of them here. And then the parasitic delay, I only want the thing people frequently mix up here is I only want the delay of that first inverter. I don't want the delay from here to the outputs here. I don't want that. That's not what that's asking, because that would be the delay of the 2 stages, not the delay of that driver. The second stages are only loading the prior gate, and so they're adding the capacitive load. So the parasitic delay is 1. So that means the stage delay is GH plus P, or 1 times 4 plus 1, or 5. And again, here you can say, okay, if in 180 nanometer, it's about a 60 picosecond tau, then that's about a 300 picosecond fan out of 4 delay. So it's just a ballpark. Does that hold true? Modern technology is not so much, but it's kind of easy to calculate. It gives you a kind of a high level view of what it is about. All right. Now, what if we now consider a path? So here's where we've done an oscillator with multiple stages. What if it's not inverters and it's logic? This is something you run into when you actually have you're doing some computation, right? Well, I'm going to define the same things, except I'm going to define these terms on paths. And these are going to be capital letters now instead of lowercase. So I'm going to define the path logical effort. That's the product of all of the G's on the path, right? So this here is product. It means I multiply. It's similar to when you do this is sum. So it's the less common one that you see. You see sigma for sum frequently, you see product less often. So if I take all of the logical efforts on a path and I multiply them together, that's how much logical effort I do on that path. How much logical work I do compared to an inverter, or a set of inverters. I can also have the path electrical effort, except I'm going to define this as the final end of my path and the initial start of my path. What are the ratios of those capacitances? Nothing in between. So C out of the path and C in. So in this case, the C out is going to be this capacitance here. Everything is in unit inverters. This capacitance is 20 inverters capacitance. This input here is 10 inverter capacitances because it's a size 10 inverter. So the electrical effort of that path is going to end up being 20 over 10. Everything's normalized. Yes?
How come it isn't a summation between each logic gate?
Why isn't it a summation between each? Because again, we're going to kind of go with, like we calculated all these other ones about how much worse they are than an inverter. This is how much worse is this than a chain of inverters, right? Because the simplest logic path you can do is just inverter, 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 an oscillator, or without feedback, right? So how much worse is this than a chain of inverters? Because if you can redesign your logic as just inverters, that's the most efficient logic you can make. Not very useful, but it's most efficient. And so then we're going to also do the product of these, where we had F before, which is the path effort. So this is how much logical effort and electrical effort we do on the path. Now, can we do exactly that? Well, there's one wrinkle to this, and we can't quite do it. We have to think about branches, because we always have things fan out in circuits. And if you think about something like this, let's say we have an inverter fanning out to two inverters. There's two paths through this. By adding this other path, you're actually increasing the amount of work that needs to be done computing. Because let's say we have that first inverter driving something. It's driving, say, the bottom path, but it's simultaneously driving the other path, so half the work is on the path we don't care about, maybe. So if we do that, we end up with this problem where if we figure out g of this, it's going to be 1, because each of these has a g of 1. Let's just do it by example. This is g equals 1. So this is 1 times 1. That's the path effort of the blue path. If I look at the electrical effort of the blue path, it's 90 over 5, 18. G times h is 18. But the problem is, if I go through there and I compute those kind of independently, what's going to happen is, when I actually figure out the h of this first one here, h, this is 30 over 5, right? Because it fans out to two size 15 gates. One of those is on the path we care about. The other one's on another path that we're doing extra work to not help our blue path. So that adds to this value h1, which is electrical effort of 6. And if we compare, then we have the electrical effort of the second path. This is 90 over 15. So if we then multiply this out, and instead of doing big G times big H, we do the little products. G1, G2, H1, H2, we get 36, which does not equal this. So we did the same computation, except instead of doing the path electrical effort, we did stage by stage. And we were off by a factor of 2. That factor of 2 is because of the branch. Because half the work we did on that other branch didn't help the blue path we were considering. This makes this whole method a little hard to do in general, but in many cases it can still be used. So we define one more term, the branching effort, which is for every gate, it's the amount of on-path capacitance and off-path over the total on-path. So, or what ratio of capacitance do I have compared to the on-path capacitance? In our previous example, this was 15 plus 15 over 15, or 2, on the previous example. And then we just multiply it by G, B, and H. So we then have this formula that includes the branching effort. So don't worry too much about branching. We're going to see some examples here. Now, we can then use this to figure out delays of paths. So if we have a path delay, we can figure out the effort part. This part is just the sums, so again, sum, not product, of all of the Fs of every stage. This is the variable part of the delay. What do I mean by that? So not the parasitic part of the delay, but the part of the delay due to the fan-out capacitances. I can sum those up to get the variable part. I can also sum up all of the parasitic parts to get the path parasitic delay. And then the total delay of the path is the sum of those. I can also do this as the sum of Fi plus Pi. Same thing. Right? I'm just summing each stage. And this is the previous thing we spent the first half or so of the lecture on. Right? Or this is also written as Gi Hi plus Pi. Okay. Here's a review of all of those terms. As I mentioned, lots of definitions. Here's a good table to put on your note card. Okay? All in one place. It's not meant to be a surprise. These are the terms you'll use. Again, it's in the paper as well. Now, let's do an example. Or let's try to think. I don't want to jump into the next part quite yet. Let's take a 5-minute break. Absorb this. So 40. Let's turn off my mic. Okay, I'm going to go ahead and get started. I'm actually going to go a little bit out of order in the next slides because I'm going to try a different thing and see if it makes a little more motivational sense. So I'm going to start with an example I had towards the very end of my slides. Let's say we want to compute, for example, an 8-input AND operation. AND of 8 things. We know 8-input AND is really slow. Here's 3 different ways we can do an AND. One on the left, we do a giant 8-input NAND gate followed by an inverter. One in the middle, we have 2 4-input NAND gates followed by a 2-input NOR gate. Third one, we do 3 levels. We have 2-input NAND gates, 2-input NOR, 2-input NAND, and an inverter. 4 stages. Which one's better? Second one? Why? The answer is depends. Now, what does it depend on? Well, the thing I didn't tell you is, what is the output capacitance? Depending on what that output capacitance is, it differs. But I can tell you one thing, one of these is worse all the time than the others. Now, how can we do that with logical effort? Let's look at this. What is the delay of each of these circuits? So first of all, figure out what is the delay or the logical effort of each of the gates. We know for a NAND gate, it was n plus 2 over 3, I think it was, right? So it's 10 thirds. I just looked it up on the table. Or you could size the 8-input NAND and figure it out. And it has an inverter, so it's size 1, or logical effort 1. Right here, that corresponds to that. Now, what about these other gates? Well, this is size 2. This is actually 6 thirds, just simplified. And then this is 5 thirds. 2-input NOR was 5 thirds. We did that computation in class earlier. Then we did all these computations in class as well. So 2-input NAND is 4 thirds, 2-input NOR is 5 thirds, 2-input NAND is 4 thirds, inverter is 1. What is the delay of each of these then? Well, I can actually do that same computation for each of these. I'm doing exactly what I did before, is I'm doing the sum of the GH plus P, essentially. Right? Logical efforts, product times H plus P. Now, what is my square root? What am I doing here with the square root thing? Well, let me jump back to something. Now, if I want to, this is basically my delay of each of those things, right? The delay plus the parasitic delay is total delay my thing. Now, I want to make an observation that I have this effort. So it's logical effort and electrical effort. Effort is work. That's what it's meant to be. It's meant to be work. I want to distribute the work among the different gates. So I want to distribute the logical part of the work and the driving of the capacitance, the electrical part of the work. Some gates, within a gate that competes, right? An inverter is really good at the electrical work, but very bad at the logical work. Well, I guess it's 1 for logical also. But NAND is going to be better at the logical work than an OR, but worse at the electrical work than an inverter. So they all have kind of these ratios of how much worse or better they are. But when I compute this kind of delay, and if I compute the effort of the path, I want to distribute the work proportionally to minimize the total delay. And how can I do that? If I evenly distribute the work, I'll get the fastest circuit. I want to assign electrical work to things with low logical effort, and I want to assign low electrical work to things with high logical effort. Think about this. I don't want my XOR gate to drive a big capacitance, because it's bad at it. I want my inverters to drive a big capacitance. So I'm going to divvy that up proportionally. How do you do that? You can basically take an nth root to divide something up into n stages. To give us the minimum. If I take the nth root of f, that'll give me the minimum value. F, we're going to call it f hat. That's the ideal effort of each stage to get the minimum delay. I'm not going to go through the derivation. I have it in here. It's actually very similar to the derivation I did of the optimal number of buffers in the last lecture. It is the same definition. So they do some calculus, they do a derivative, and they come up with this. You can take this nth root. So I want to make each stage have this effort by sizing it appropriately. Well, the first thing I can do is say, well, what is the fastest I can make this path by assuming everything exactly bears that amount of effort? Well, I just substitute that back into my equation. I have n stages times f hat equals p. So this is n stages times f hat plus p. This part's constant because my logic doesn't change, so I can actually kind of ignore that. So n times f hat, or n times the nth root of f, gives me my fastest delay of these n stages, given the path logical effort and the path electrical effort. What can I do down here? So I'm going to go back to my example I showed. And so that's what I'm doing right here. So if I look at this, I did the exact same thing. I figured out g of this right here. So g times g of these is 10 thirds, equals 3.3. What is g times g of this? Well, it's 2 times 5 thirds, or 10 thirds, right? What is the product of this? Well, it's something. I'm going to multiply that out. What I'm doing there is, I'm then doing that g on the previous slide. So this is 10 thirds. Here's the other one, g, 10 thirds. Here's the product of that, all those numbers, g, times h. Now, what is h? I'm leaving it unknown. I don't know h yet, because as I said, I didn't tell you what this is, and I didn't tell you what size this is. So I don't know yet. I'm going to pick the sizes. I'm going to pick the sizes for the best delay. Well, I formulated this as the nth root here, and then this is gh, so this is the nth root. And here again, this is the nth root as well, because this is my f hat, right? This is 4 stages, so I take n equals 4. This is 2 stages, n equals 2. This is 2 stages, n equals 2. Oops, n equals 2. So for the one on the left, I take the square root. For the one in the middle, I take the square root. For the one on the right, I take the 4th root to make sure that I balance the effort among the stages equally. There's 4 stages on the right side. I want each one to bear a 4th root of the effort compared to the others. And these other 2, I want the square root. This is the fastest delay we can get if they perfectly balance that. It's independent of the fan outlet, because I don't know h. I'm showing it in terms of h. What if I plot this? I have h on the horizontal axis. So again, kind of, this is fan out of 4, right? Then I have fan out of up to 25 over here. Well, interesting things. Option 1, which is the red line, has a higher delay than option 2 always. Why is that? Well, it has this horrible NAND gate, whereas the other one has 4 kind of mediocre gates, divided among 2 stages. They're better able to divide the effort of the electrical effort because they all have more equal logical effort. Never use the left one. Sometimes use the middle one. When do I want to use the middle one? Well, there's a crossover point about right here. And what is that crossover point? Well, it's about an h of 6. So what that's saying is, whenever I have a fan out of about 6 or more, option 3 is the best, the one with 4 stages. That's because I can ramp them up. Remember the exponential horn I did with the sizing? I can basically do something like that and kind of divide it up proportional to the logical effort of the gates so that it drives them much faster. another way to phrase it, I'm dividing the work among 4 levels instead of 2. Dividing it among 4 is much better than dividing it among 2. So for high fanouts, the right one is best. For low fanouts, the middle one's best. Yeah.
In the next slide in the graph, it implies at 0 that the option 1 and option 3. Does that ever happen in reality? And if so,
Yeah, so what does this mean?
fan out of 0.
Fan out of 0. They're not driving anything.
So it's like doesn't really exist.
Yeah, it wouldn't really exist. That's basically only considering the self-loading of all the gates, I guess. Yeah. Well, yeah. Yeah, unless it drives something, you typically wouldn't go below a fan out of 1, right? Because a fan out of 1 would mean maybe it drives somewhere to a single inverter somewhere, a single minimum size inverter. Yeah, so this is the type of thing you can do with this, is you can say, oh, those are the trade-offs here. Never the left, high fan out the right, less than 6 fan out the middle. I had to do a 4th route. But other than that, it's just a linear equation. I didn't tell you what the sizes are still, right? What size should this gate be? What size should this gate be? Well, we can do that with logical effort too. So that's the next example I'm going to show you. Well, we can figure this out because we know this f hat. That's how much effort we want each stage to have. We take the nth root of the big f value. We know that f equals g times h, logical effort times electrical effort. We know that h is equal to c out over cn. I'm going to take this equation, and I'm going to solve it for cn. So same equation, I take g times c out over f hat gives me cn. Just some algebra. But what is this saying? What this says is, if I know my output capacitance, I want to solve for my input capacitance. And what do I do that? How do I do that? Well, I do it dependent on this factor right here. What is the ratio of the logical effort of my stage compared to the ideal effort of the stage? The ideal effort I want. If I have a big G, I want to have a small Cn. Or if I have a small G, I want to have a big Cn. So I want to pick the sizes proportional to the relationship of my logical effort and the ideal effort of the stage. Does that make sense? It's kind of like, so again, if I have a simple gate, I want it to drive more. If I have a complex gate, I want it to drive less. A simple gate means G is small. An inverter is 1. A complex gate means G is big. An XOR gate has 28. Well, if my F hat is like going to come out to like 8, I want to have the XOR have almost as little fan out as I can. And I want the inverter to have all the fan out. So what we can do is we can work backwards and size gates because we assume that we know the fan out. You can also work forward from the first gate, but you have to start from one end to come up with the solution. So let's go with I'll do this example, even though this has branching. No, I'm going to skip this one. I'm going to go to this one. I have 2 examples in here. This one's better because it has no branching. So here I have a path. It's an inverter, a NOR gate, 2-input NOR gate, 2-input NAND gate, another inverter driving an output load. For every one of these problems, we're going to assume that we know what it's driving. So this output is some fixed value. We're going to also assume that this input is some inverter. It's maybe coming from off chip, or it's going to be some fixed value. And we want to figure out the sizes of the middle 3 gates to give us the fastest delay. Well, what is the fastest delay, first of all? Well, I can just go through and I can find the logical effort of each gate. We know an inverter is 1 on the left here. We did this one that's 5/3 because it's a NOR gate, NOR 2. This is 4/3 because it's a 2-input NAND gate. Here's another inverter, right? We did all those previously. So I just do the product of them. So this is the product, not the sum. It's the product of all of the G times I. Right, 1/3 times 5/3 times 4/3 times 1. It's 20/9. What is the electrical effort? Well, here I just look at C out over Cn. The C out is 20, the Cn is 10, so it's an electrical effort of 2. It's not a big electrical effort. It's normal. It's less than fan out of 4. It's normal. Again, no branches, so we can assume this is B, is 1. Branching, I have another example for branching coming up. Now if I figure out the path effort, it's the path logical effort times the path branch effort times the path electrical effort. It's just the product of these 3 things. So it's 20/9 times 2 is 40/9. Right, 20/9 times 2. And because I have 4 stages, I take the 4th root of that. So this is the 4th root of 40/9, which is about 1.45. And so this is F hat. So I want each stage to have an effort of 1.45. What is that? An inverter has an effort of 1. So about 50% above an inverter's delay is what I want each stage to do, right? Just to kind of bring it back to sanity. So not quite inverter, but 50% compared to a little inverter. Well, how do I figure out the sizes? So start with F hat, or what is the best delay I can do? Well, I can figure that out without even figuring out the sizes. I just take n, number of stages, times F hat, plus all the parasitic delays. And that gives me my best delay I can do with this entire thing is 10.8. 10.8 inverter delays. Right? That makes sense. I have 2 inverters, but then I also have a couple logic gates. Those add like another 4 inverter delays because they do work. So the whole thing is about 10 inverter delays. How do I size it to get those? Well, I work backwards. I start with F hat. I can first solve for the last gate, the last inverter. And I want Z. I can also call this like C in of Z. I'm just going to call it Z. But that's the input capacitance of that inverter, which is also the size of the inverter. Because remember, the input capacitance of a gate is proportional to S times CP. So I kind of use the size interchangeably with the input capacitance. So what input capacitance should that inverter have? Well, I take the output capacitance. It's the formula I went back up here. It's C in equals GI C out over F hat. And I apply this over and over again for each of these stages. So what is the C out of the last inverter? Well, it's 20. Right here. So it's that. What is the G in of the last inverter? Well, here, it's that. And what is F hat? Well, it's that. So I did G times C out over F hat is this. That is now the capacitance here. This is 13.8, because that's Z. So now I can solve for Y, because I know the C out of Y is going to be 13.8. So what I do there, I substitute that here. I know that the logical effort of this gate is 4/3, and I know F hat again is 1.45, every stage, 1.45. That gives us 12.7. So now that's 12.7 right here. I can now solve for X. I do the same thing. So here's my 12.7. And then this gate is 5/3 logical effort, and again, f hat of 1.45. So that means the input of the x gate is 14.5. Now if I go one more stage, it actually works out that I get 10. So 14.5 divided by the logical effort of 1 divided by f hat gives me 10, which is the same thing I had here. So what I did is I evenly divided the effort among each of the stages. And that, how I divided it is the value of each of these capacitances up at the top here. So it's this, x equals this, y equals this, and z equals this. Now, those are going to be my sizes of my gates. So what are the actual sizes of the transistors? Well, remember, go back to my, and I drew it kind of on the bottom over here. Remember, we scale all of these by s. Right? For an inverter, the PMOS is 2s, the NMOS is 1s. For an AND gate, the PMOS are 2s and NMOS are both 2s. And for a NOR gate, the PMOS are 4s, whereas the NMOS are 2s. So I go through and I want to then divide that capacitance proportionally. So we know the final gate, this Z, 2/3 of the capacitance should go to the PMOS. 1/3 should go to the NMOS. Right? If you look at just the equation right here, 2/3 is the PMOS, 2 divided by the total input capacitance of 3, and 1/3 is to the NMOS, 1 divided by the total input capacitance of 3. I just split it up, the PMOS and NMOS. So I end up with the PMOS of size 9.2, NMOS of size 4.6. What size gate is that if I just want to pick an S? Well, that's S equals 4.6 for that inverter, right? Because NMOS is 4.6, which size 1 has a value of 1. Does that make sense? Kind of. Now, I can do the same thing for the NAND gate, except here 50% of the capacitance goes to the P and 50% to the N, because the PMOS had size 2 and the NMOS have size 2. So I divide it 50-50. And I come up with 6.35. What size NAND gate is that? Well, it's 6.35 divided by 2. So it's 6.35 divided by 2. It's about a 3.17 something x gate, like a little over a 3x gate. And then I can do the same thing for the NOR gate. Divide it proportionally, and I can figure out the size S. And then same thing for the 10. I divide it proportionally, and I come up with a size 3.3x gate. That's the fastest circuit I can do. Now, what happens if I have a library? Well, I don't have a size 4.6 gate. I could probably pick a size 4 or 5, or maybe a 4 and 8. Depends what's in my library. You round it. You know, size 3.17, I'll probably go to 3. Luckily, if you do that type of thing, you're not far off from optimal. Actually, this is number of stages, but if you do the rounding sensitivity, you're not far off if you round, because things end up working out pretty well. Now, I'm going to leave it at this. You can revisit this buffering example I showed through and I enumerated last time, and you can figure out the optimal delays given what I told you.